Okay, guys. So, this is our second lecture. So, I was asking you to do something at home. Did you try? Anyone try anything? Okay, I will get back to that point later on. So, you already know what's the goal of our whole course, and it's the second objective of our second lecture. So we're going to learn today model and thinking relation understanding, how the model and thinking actually have relations that we'll understand a little bit more. I think in the first lecture, we also have learned something, but that was not so precise. So I'll try to give you some kind of precise understanding on model and the thinking. Then we're going to learn thinking and systems engineering as domain relation understanding. So why we need systems thinking and how it's related to systems engineering domain, that we'll understand. Understand the necessity of system thinking for model-based systems engineering deployment. So one is for systems engineering, one is for model-based systems engineering. So get to know a collaboration platform Git. So how to use the Git repository for this course. Sabina will talk at the very end of the lecture. So let's see. Okay. The first thing, emergence of model and understanding the complexity. So why we need to have model and how it's gonna help that we're gonna learn in this one. So let's say you are designing something in a group. So maybe I think mechatronics example would be nice. So let's say you have two different disciplines. Let's say discipline one is mechanical engineering and discipline two, why the thing is not coming? Okay, so discipline two is, I don't know, software engineering. So you see how when we are thinking about something, about some solutions, so first thing actually comes to our mind, the original thought. So this is really very abstract. As soon as you are not writing somewhere or discussing with someone, then you do not have proper understanding that what you are thinking of. So in that level, we know, somehow when we are discussing, or maybe we make some sketch, we know this is a mental model. So sometimes when you are talking with other engineers, then maybe they understand sometimes, maybe they do not understand sometimes, because different engineering domain have different way of understanding. So then when we make a formal model, let's say from the mental model to a more formalized way, let's say we can make a sequence diagram that something comes one after another, then something after from the second level to third level. Then if you could describe those things to an engineer, then he could understand those things, I think, a little bit better. And this is actually the first point why we need model-based systems engineering. I think this information model, because in this information model, if you really understand the problem properly, I think if you wanted to do a CAD model, that is, I think, more explicit. That actually you can deploy the real requirements there. And you see, when we have the original thought, so things are a little bit very complicated because it's really ambiguous because the knowledge is not developed there. There is a triangle for knowledge, like data, information, then knowledge, then wisdom. So there is a hierarchical rank. So something like this. So very early stage is the data, then information, then we have knowledge, wisdom. So I think if you read some books on what do you call, some psychological books, like in ancient time, they are actually developing knowledge through discussion, through dialogues. Okay, so what we actually try to emphasize in this model-based systems engineering approach. So here is the most important part of model-based systems engineering. So we have to transfer the real understanding through model to the other engineers. So this is actually the whole thing is from Paul Byte's books. It's Pulse Byte, something like, it's a German book. I think 2003 they published this book. So so why we need actually model, and where is the complexity? So I think it gives some sort of overview. Okay. So significance of models. Now we in the first lecture we understand, or I already asked you, like, what is model? You gave your own definition, and we also have seen the that what could be a model in the model-based systems engineering approach. So a model is a simplification of partial representation of reality in order to accomplish a task or react on or reach an agreement on a topic. According to Fredantel, a model is the representation of one or more concepts that may be realized in the physical world. So some of you told that model is supposed to be the presentation of the physical product. So this is somehow the same definition. Then Mr. Dory, he says model is the abstraction of a system. So he didn't tell that the system is supposed to be the real system. It could be any type of system. So if you have a digital system and if you have the model, so I don't know. So this is a little bit not too explicit to me, but model is an abstraction that is very clear. And then again, one model is in principle provides consistency, in particular by synchronizing the graphical symbols present in the diagram with the elements of repository. It is important to bear in mind that diagrams are only a representation of a point of view. The diagram usually constrains only part of the elements constituting the model. So here, I think described very well, like what's the difference between a model and the diagram, because now what I have done here is it's a diagram, right? It's not a model, because model, in terms of model-based systems engineering, it it carries some value. So that we will see in the next slides. So in model-based systems engineering, model is a channel of communication across domain and machines. So if you wanted to develop something, you need people and you need machines. So if the machines does not understand your model, then I think you cannot really transfer your thoughts through machines to other people. So that is, I think, the biggest challenge in model-based systems engineering, because it is somehow tool-based engineering, and therefore most of the models are not really understandable by different tools. So if one tool made some models, other tool actually do not understand that. Okay, so the ultimate goal is yields rational understanding. So models supposed to make things clear, not making things complicated. Any question? Because I think this part is really important. If you have any questions, feel free, we can discuss, because this is a practical lecture. So if you have any type of question, don't think like this question is stupid. So no question is stupid. So all question is important. Feel free to ask if you have any question here, because I found understanding model is a little bit difficult. It took really long time for me to understand. So if you have any question, feel free. Or later part of the lecture, if you have any question, feel free to ask. So here is a little presentation, like how the model is different than this is a PowerPoint one, and this is a SysML based tool, CAMU system modeler. So you see in the PowerPoint one, there is no syntax. Sorry, the concrete syntax is something like here, and this syntax has a semantics. So semantics is something like, when we are talking something, let's say a man could be a semantic, and a kid could be a man, I don't know, a boy could be a man. So when you're telling to your computer that a man, he could think of anything, a boy or a kid, but you have to define beforehand what exactly man means to you. So this is the semantics. Behind the scene, there is something, and that actually has some value when we are trying to combine two different models or two different tools. Then you're gonna learn this thing, I think, little bit more explicit from Sabina in later
Yes.
Lectures. And this is, I found this is also a good example of like different types of model. So you see here in this direction is ease of communication and accuracy. So accuracy here, actually the author describes how explicit to the person whom you are describing or discussing the model. So you see that when we are writing the mathematical model, of course, it's maybe a little bit difficult for a social worker to understand this one, but maybe for an engineer, it is very explicit what it's meant to say. If we show something like this, that is also very explicit, what you wanted to say through this specific model. And you see when you are making different types of diagrams, the level of accuracy is actually going down and age of communication is going up. So this is a good presentation, I would say, to understand the model. Any question here? Okay, role of a model. Model to communicate. We have seen previous slide, and model to simulate. So normally it's really hard to distinguish in model-based systems engineering when they are talking like even though if you see some videos from enterprise architect or Cameo system modeler, they are talking too many times with simulation. They are really crazy about simulation, and it's a little bit hard to grasp the idea behind that, why they are talking about simulation, because simulation is kind of a way of analysis that gives you some kind of solution that let's say 1 + 1 is 2. If you could simulate this one, it gives some kind of precise observation to your fellow mates or engineers whom you are developing the things. And here you see this is this picture is actually taken from the book. It's published 2019. So this is a robotic arm, and you see this is a CAD model and this is a CSML model. So in different model actually describe different situation, different views. So here, if we read it, model to communicate, to institute rational understanding across different stakeholders and engineers domain. It could assist engineers for decision making. So model supposed to help the engineer for decision making. It is not only exchanging or exchanging information. The student, the engineer is supposed to make decision out of the model. And the model for simulation, for model to be executable, the model language need to have a semantics precise enough to allow it. So semantics and syntax that is the somehow related with linguistic, and this is our specific area. So you guys gonna learn a little bit more maybe with the semantics, like why syntax and semantics is really important for modeling later part of this course. So I'm not gonna make it like more complicated. And purpose of a model. So this is, I think you can read it through. It is more or less what I have described in the last slides. This is kind of summary. And this is, I think, a very interesting question to me, that why do engineers love to like the model? So reality is often too complicated to deal with directly. Abstraction hides complexity and facilitate analysis. So that is why, in this modern age, model-based systems engineering, I think, is, everybody wants to apply, but there is no specific solution so far. So model provides cognitive leverage. That is the summary of the talk or this slide. And here you can see, or you can visualize how we can actually understand the models and the systems. So what's the relation between the models and systems? So I think you guys have seen how the construction work going on, right? Somewhere. So for the construction, let's say if you wanted to build a house, what do you need? So you need some rods, some cement, some bricks, so all the raw materials. So through systems engineering, we try to actually build a system that actually somehow fulfill your requirements or the system requirements. So if you think like when we are doing different models, let's say I was talking about the SysML models or CAD models or simulation models. So those are the models we have to do to build an efficient system that somehow meet our requirements. And here you can see there are different types of model we're gonna need to deploy a system. So let's say here SysML models, CAD models, 1D models, simulation models, FMI is actually a model transformation interface. Like different, you can exchange different models there in their network, and they support really good numbers of modeling tools. But yeah, most of the time this is really not making sense because yeah, many tools they are not really still supporting. Also, the consistency and uh, like communication between the tool is still very difficult with this FMI. Do you have any idea with the 1D simulation? Any of you heard about 1D simulation before? Okay, just to give you overview. Simulink, yes, Simulink could be 1D simulation, yeah. But there are some other tools, I think very efficient tools. I forgot the name. There is one tool from Siemens. There is one tool, yeah, Daimler from Modelica. Yeah. No, the company name Dassault System.
Yeah.
Right, Modelica also from them. Right. So these are the tools. So 1D simulation tools is pretty much, I would say, like the SysML tools. You could make some diagrams. You could assign some properties, and you can simulate that. So the difficulties is somehow like what's the model name, Sabina, in SysML we are using for analytical, like for parametric diagram, right? So parametric diagram, it's quite similar, like 1D simulation and parametric diagram. There are many similarities, but the tools are really like quite complicated, honestly speaking. Because if you wanted to learn this and apply for your product design, I think it takes really long time. Okay. Here,
the reason for this, why is it? The reason is that most of the tools which are providing models try so many different complex things, and so the tooling itself is getting complex. That's why you have this high or below the tooling. What we want to learn you here is a little bit different perspective of it, because there are so many different tools, but you have to have the right view on it. So the view is that you get an overview of what you need to solve things from the early phases of production cycle until the end of the product, so that you really have a look on it and not say, okay, I have to use this tool. But I say, okay, I want to model, for example, I don't know, the structure of my system, and therefore I will need this and that. And then I will choose from the 100 different tools, the tools what I can use best for this purpose. But
So then the next one. Uh, she told just now views. So uh, actually, to to make you guys understand or give you some overview, you will hear, I think, 1,000 times in your career when you're gonna do model-based systems engineer. Even though I think every single book, more or less, I have found like the views and viewpoints. So these very important things in model-based systems engineering. So the views and viewpoints are really very important because some problem people sees differently, you know. So she has a famous example. Should I tell that? She was working with some of these fellow mates, and she took almost 6 months to understand her what she was talking about, you know. So because I think her background was from mechanical engineering. Yeah, and her so you see, this real example in front.
And therefore, you have this modeling already and the modeling is just the browning. That if you say this is a class, the other person also understands what you say because the modeling language is the common. And if you do not know the context, then it is really complicated. Because when we talk about model, you don't perhaps understand thinking model, and then you talk native and perhaps have mind. It could be also the same what we are talking about, but most of the time it is not clear we talk. So when you are talking about, yeah, I need this property here, and I want to change the length of this, I will answer no, it's not a property. But then we are database and we change the value. So this is the first thing you have to think of. If you work on interdisciplinary approach, then you really have to think of what is the viewpoint of my colleague. And then you can get started. Most of the time, problems exist because of communication.
Okay. Here you see model have views that are represented in diagram, but the model is. I think we can close this one. Okay, but the model is unique. So here you see two SysML diagram. So do you have the know-how with the SysML? Because I think yeah, but I think I'd like to give them a little bit overview. So SysML diagram. SysML is, itself is a language for system modeling language, the full abbreviation. And this has been created, I think, since 2003, and the first. And it started 2003, and 2007 was the first version that I wanted to tell. Yeah, and I think there are several versions, 1.1 something something. I think up to 7 right now.
Right now,
6.
7 and currently
Okay, and the SysML version 2 is coming. We are hearing since long, but when it will come, it will not yet. But interestingly, if you are interested about the SysML2, there are some German guys. They have some YouTube channel, and they're talking really a lot about the SysML2 and how it gonna work and how it actually resolve the problem of SysML1. They are talking really a lot.
But first question from our side. Do you know any modeling language? Do you heard of it?
I think
No. You? Yeah. Okay. Okay. AutoCAD. Okay. More or less, they are using different languages.
and not directly. Yeah.
You? Okay. But Modenica? No? Or UML? No? Okay. So you will learn. No problem. The question has also from our side because we need to know also for our assignments.
Right.
Modeling languages you will hear also in the from Remote we already started today. It is one of the foundations for model-based software engineering, and based on this, it is established to model-based systems engineering.
Right.
And in modeling languages, you can define a complete notation, a complete syntax that belongs about abstract syntax, complete syntax, and abstract semantics, so that you have the same viewpoint on the system you are developing. And SysML, the systems modeling language, comes up out of UML, Unified Modeling Language, which is one of the most used standards in software engineering for modeling. The Unified Modeling Language really defines in an easily way the structure of software architectures and also behavioral models. And based on this, systems modeling language established because there was a discussion always about UML, where you talk to systems engineers, who say, well, okay, it's just something from informatics, and they want to push us to that. And therefore, the concepts are not really familiar for the system engineer because, for example, in programming languages, we always talk about classes and everybody knows what it means. But in systems engineering, we talk more about components, blocks, and so things like this. And therefore, they established the system model, which was quite similar to the UML, a little bit smaller, and a little bit extended to things which are important for systems. And based on this, it has the problems of UML. And that's why they started the initiative of SysML 2.0, where they want to shift away from UML. Will we are not for the same, for really solving problems. And as the site already said, it is discussed very, very, very long. They started in 2018 to discuss about SysML 2.0, and now currently trying to get the first draft in line.
Right. Yeah. So one thing is actually, I think you're gonna learn, I think, later on from the video, not from the course. So in modeling language, there is some options to give some instruction to your system that, let's say, if clauses, and there are some clauses, you can use, but in this SysML language, there is no option to write something and give your system some instruction. So they also try to introduce this kind of user interface into SysML 2 whatsoever. So this is not the class for SysML. this, you see, this is two different SysML diagram. So this is, I think, BDD, no, sorry, internal block diagram, IBD. So there, I think BDD and IBD. So um, block definition diagram and internal block diagram, because SysML has how many classes? 9. Okay. So there are 9 types of different diagrams you can do, and they have different use cases. So this is same diagram, but in different way they expressing this one. So why I bring this to show you like how the view and viewpoints actually differ in system design or system architecting. This is somehow you can call system architecture. So how you are designing your whole system. And this is actually, there is a framework. This is not so important, but just to give you some understanding how you're gonna use some frameworks for designing your product through SysML. Because with the framework actually giving you some guidelines that you have to do this and that for that. So some sort of rules, some sort of abstraction you will find. But most of the time, I have seen that they're really complicated, and who made the framework, I think he also didn't understand what he made. Most of the framework is like this, because there is no concrete examples from the framework. Maybe part of the framework there is an example, not the whole framework. Like from the top view, you cannot really magnify the problem very core. So this is also another complexity, but I think yeah, this is an ongoing problem, and Professor Seman also sometimes said when he started CAD, I think since 30, 40 years back, he told like the CAD program also like this, and there were many problems, but now you see CAD program is really very cool. More or less, you can do many things with the CAD, and I think it's more user friendly. Even though when I started CAD, it was same like the Python. We have to put some kind of instruction. So, and AutoCAD was only the CAD model, and other CAD model was not really so known and popular, and nobody knows about it. So things are improving over time. So I hope they also improve. And I think Savine, you already know since long SysML, and you already know UML. I think right now there is a big shift, right?
Yes.
Yeah. Okay, then this also you know, but I try to make some example out of this, like systems engineering domain. So normally we have, when we are you know, thinking of some problem and solution, so there are normally 2 domains we are dealing with. So problem domain and solution domain. And sometimes not sometimes, I think systems engineer most of the time you know, come across to the implementation domain. So the problem domain may be urban traffic cognition. So let's say somewhere there is a huge amount of traffic, and in the solution domain, you're supposed to figure out what's the possible solution. So here is the solution, maybe undergo transport system to relative to the congestion. So this is the solution you are thinking of, but when you are trying to implement, you will see there are different types of solutions coming. Like implementation domain includes tunneling, or you can make another road on top of the existing road, temporarily diverting the surface traffic, or maybe you can make some sort of U loop or something, and you know, try to divert the traffic in different direction. So in implementation domain, like sometimes when we are in the solution domain, we are thinking something, and when we are coming to implementation domain, the world is really very different. So more or less in the systems engineering, we are dealing with problem, solution, and implementation domains. So just to give you the recap from the first lecture. Okay, here a little bit more context of problem and solution. So in terms of systems or model-based systems engineering, you see the problem is kind of user requirements. This is actually the problem, and the solution is system requirements. So you define what you're gonna need for giving the solution for your system. Then describing the problem and its context. And in the solution domain, abstractly represent the solution. So this is actually how we are doing the modeling. Describe the stakeholder expectation. This is the problem. So I think this is also from a book, and I think in terms of order, this stakeholder expectation will go up, because without the stakeholder expectation, you cannot find the requirements. So this is more or less the needs and the assignment that you're gonna get. That will have some sort of scenario like this, and I think for the assignment, you're gonna also use some of the slides. Okay, then do not define the solution, but the context. So Sabina also told sometimes back the context of the problem. So to make your fellow engineers understand, you have to understand the context, like based on which context you are making your model. That also need to be defined. And in the solution domains, do not define the design. Specify the quality of result based on what you're gonna justify your system. Then specify quality of execution. So how you're gonna execute those evaluation. Created by stakeholders, created by systems engineers. So this is, I think, the most important thing. So problems mostly created by the stakeholders, but don't be confused with the stakeholders, because the stakeholders have so many definitions, and more or less here, stakeholders means the customers. So when you are working in a team, according to the definition, I think everybody, like the engineers, the management team, the customers, everybody is the stakeholder for a project. But here, they normally in the book, when it is stakeholder written, normally they are try to relate customers. Okay, and systems engineers, maybe you're gonna work as systems engineers. Okay, so this is also very important, and it's also a little bit hard for me to understand. That's why I also bring this one here. And I think in the first lecture, you also have seen something, synthesis, analysis, and what exactly, I didn't give an example. So to give you more overview on this, I just made this slide. So synthesis is an act of combining constituent elements of separate materials or abstract entities into a single or unified entity. Synthesis has the goal of yielding a new, whereas integration helps to complete one whole. So here, what do you think? Which one is the synthesis, and which one is the what do you call integration? Anyone? Which one is according to the definition? So answer is here. So synthesis is making a whole, sorry, a separate entity, and integration is making a whole. Like, let's say, I don't know, if you have a robot and one hand or leg is not is missing in the robot. So what do you think? Like, if you put the missing part, then it is making the whole, right? And this is actually integration. So here, this is actually integration, and this is actually the synthesis. So it is making A plus B is making AV. So this is like, making a different thing. So synthesis is really a very important thing when you are in the thinking level. Then you have to think really like in a water, and don't be mixed up with integration and synthesis, because they are two different meaning. That's the main reason why I put this one here. Okay, so this is actually the first part. So this is the last part of the lecture. So what do you think actually? What exactly thinking means to you? I think it's very lame question, but like if I ask you, anybody would like to share his pain with me? Yeah, please. Right? Anyone? So the ultimate goal is like thinking we need everywhere. Like when you are sitting down, when even though you are going to toilet, you also need to think. When you need to open your laptop, you need to think of your password. So without thinking, you cannot do anything in this whole world. This is different because I can open the laptop or going to the toilet. There is and very good thinking is some new problem and I need a new solution, so I have to think about it. There are some classes of thinking, so you are talking about a little bit advanced. So overall, what I mean to say, without thinking, you cannot do anything. So, but thinking has a great value in systems engineering or model-based systems engineering, because it also tells you how to think. And I actually have different engineering background. Let's say I was studying aerospace. I was studying computer science. Now I'm doing PhD in mechatronics. But nowhere, honestly speaking, I have seen like they teach how to think. But systems engineering or model-based systems engineering is a domain where you can really learn how to think. I think this is really very amazing, because like we are doing everyday thinking. So what's wrong? What we need to do, or what we need to learn with thinking? But you will see the importance in this part. So thinking first, the action that underlies problem solving and decision making. So yes, what you? Yeah, and you see your answer is here also. So thinking can be divided into three parts. So non-systems thinking. So what you are telling right now, that yeah, automatic. Let's say I need to go to the toilet. I need to go to the university. I need to take the bus. You really do not need to calculate something, right? So this is a non-system thinking. So thinking of singular issues without considering other effects. So you see, it's systems. It's not singular. Systems thinking and critical thinking. So there are three parts, and please really very careful with the S, because the significance of your understanding actually somehow hide here. Because when you are thinking of a single solution without considering the other effect, then maybe in some point your solution could, I don't know, will not work. So as a systems engineer, you have to think what are the related problems could arise in the later part of the design. So slowly we're going to learn how this all other thinking works, and don't mix with critical thinking and system thinking. Critical thinking is something different, like we scientists, we are doing critical thinking with some specific solutions, but system thinking is a little bit different. Um, um, we'll see what it is. Okay, so
This is like system inside of the board. So the guys concept.
no, critical thinking is a little bit different. So let's say you are telling you are bringing, let's say, there is some explanation also, but this is a point of discussion. That's why I do not want to stop you. I do not want to stop your thinking. So you see, you bring a new solution or a new theory because you have seen there is some problem with Einstein theory of relativity, and you bring some new thinking, critical thinking. This is actually a critical thinking. It is not system thinking, because somebody has done something and you find some fault, and you re-evaluate the things and bringing a new solution. So what I have told, like normally in scientific world we are using critical thinking. So maybe you will hear that people will tell, yeah, a little bit, think a little bit critically. So critical, but we are using without understanding. So I wanted to make you a clear understand. I would like to deploy the clear understanding of system thinking and critical thinking. So in systems engineering, normally we are not using critical thinking. So we'll see what was the different.
System thinking is like logical thinking, critical thinking, or like creativity or something like this.
Uh, Hard to say, because creativity we cannot really define. And the second thing is logical, more or less. Yeah, logical thinking, I think this is more or less related with system thinking. But still, when you are, let's say, making a new theory, instead of Einstein theory of relativity, then also you need to think logically, because without logic you cannot make other people understand. So it's a little bit little bit confusing, but I think I can take out or I can make you fully understood on this topic. So you see, this is actually a example from a publication. So there they try to make a traditional approach how people are thinking. So they are designing a course related to sustainability, and you see this course are not really connected. They are really very different, or segregated. They are not really connected. So you see, there is no effect. They cannot analyze the effect from this course to this course to this course. But you see, when the traditional approach versus system thinking approach for teaching sustainability, have you had any kind of experience with sustainability? Did you do anything with sustainability? Because we are three people doing something related to sustainability, and okay, sustainability. Have you heard about circular economy think everywhere you see in the university. So sustainability is like we try to actually create a benchmark for sustainability, but unfortunately there is no benchmark. So we are thinking like if we use less energy, then maybe we are sustainable. Then
Do you know the word sustainability?
very good. Thank you very much. So so let's say um, recently you're gonna see if have you been to KFC? Anyone of you? Okay. Yes. Okay. Previously, you will see KFC was providing like if you take any drinks from there, some kind of cover and a straw. So now they are not providing any straw or any cover. Have you marked this? And you will see in their table there they have written that we are sustainable, we are eco-friendly. So they are actually somehow try to reduce the waste. So this is a way like you know how you are gonna use less amount of product and use somehow efficiency, increase the efficiency. So sustainability does not have any kind of measures, but there are some key criteria. Let's say um, um, we can tell Airbus aircraft more sustainable than Boeing aircraft. Maybe they are using more environmental friendly materials, or maybe the Airbus aircraft are using uh, or consuming less energy, like maybe they have efficient engine. So there is no benchmark for sustainability. Only you will see the companies are talking we are sustainable than other companies. So it is something like how you gonna reduce the total consumption and make think efficient. So this is the goal of sustainability, what we understood. And last time it was funny, like I took my mom to Vienna airport. She wanted to fly from here to Bangladesh. And, one guy was next to me, and he actually working with sustainability. Somehow we introduced and we are talking, and he's this guy also from Graz, but he was trying to fly in Australia because he was doing some consultancy related with sustainability. So I was asking him, I think I got the right person to ask the right question. He was asking me what, because previously we exchanged the information, what he is doing and I'm doing. And then I was asking, like, what do you think? Like, you're working for different companies around the world. What do you think sustainability means to you, and how the companies are using this word sustainability? What do you think? What's the use of it? He's telling me, like, should I tell you the truth? Of course. And he was telling, like, I really do not understand the thing how people are telling we are sustainable. So you see, and he has more than 12 years of experience. And he was telling also me that most of the companies, not all, most of the companies they are using as a marketing hype. That even though you will hear in the radio most of the time, like some companies are making some advertisement that we are the sustainable company, we are the circular economy company, and it is really a big topic, and there is no solution. It is like model-based systems engineering. So sustainability actually, when you wanted to think of sustainability, you have to see how we are doing the thing. Maybe later part, if you have some interest, I can show you, like we made an Excel sheet to calculate the number of what do you call environmental impact we are making by our research. So there we calculate, let's say CO2, then NOx, then different gases, what we are introducing to the environment, and what's the impact of it. So let's say if you have a office and you are using, let's say, solar energy, so you can tell them, yeah, your office is more sustainable than JKU because JKU does not using the solar energy. So this is the way how you think of sustainability. But when you are trying to measure the sustainability, where from you buy the materials, like let's say this company, they're telling that they're using solar cell for sustainability. But solar cell, you need the, what do you call the solar wafer. Then you need some kind of box. Then you should consider the transportation. And there are really, I think, more than 1,000 things you have to calculate. And most of the time, you cannot really connect what's the first point where from you will start. So it is something like one thing is connected to another. And I will go very interesting. There is a very interesting slide. There, I think there you will understand how this system thinking actually works and why we should think in this way. So here you see the environment. They're thinking of environment. They're teaching something about environment, then society, then economy, and you see there are many other things that also have impact on the sustainability, the overall sustainability. So it's a chain, like one has impact to other. So the system thinking, normally you have to think about the whole system and the related system. So this is the key thinking or key way of doing system thinking. I think this is the thing what I was actually searching of. So for want of a nail, the shoe was lost. For want of a shoe, the horse was lost. For want of a horse, the rider was lost. For want of a rider, the battle was lost. For want of a battle, the kingdom was lost. So where is the problem? You see, just a nail. Nail is the problem. So this is from a rhyme from Benjamin Franklin. And but the problem is actually the nail. Because of the nail, the kingdom was lost. And this is actually called the butterfly effect. And okay, just to give you what is exactly butterfly effect. So butterfly effect is actually, have you heard about chaos theory? Exactly. So this was, I think, proposed by Mr. Lawrence. He was a MIT professor or something. And I think the weather forecast, what you are seeing right now, everything actually coming from here, butterfly effect. So what was the observation of Lawrence? Let me tell you the story a little bit more because it's very interesting, and then this is very much related to systems engineering. So he made, I think, 12 equations to predict the weather condition. And one day he just and he also made the computer algorithm that time to calculate precisely his prediction. And one day he ran the simulation into his computer and went out for a coffee. So somehow by mistake, after a point, there will be, let's say, so there will be 6 digits, but by mistake he put only 3 digits. But you see, when we are calculating something, I think after 3 digit, after point 3 digit, this 3 digit, I really do not see any value. Most of the time we are ignoring, right? But if you do not get my point, just ask me, because this is very important. And when he come back, and he have seen like previously he calculated the same thing and it was giving different weather forecast, and now it is giving different weather forecast. Let's say previously it was showing that rainy day, now it's showing what you call a sunny day, and he didn't understand what's the problem here. So he was thinking, then he found out that he forgot to put 3 digit after point. So this is, let's say, 0 point something. Okay? So these 3 digits he forgot to put, and that's why the whole calculation is showing different, like the calculation outcome showing different. And then he actually made 3 simple formula out of this observation, and he wrote also a publication, and I think the publication name was "If a Butterfly Flap its wing in Brazil, is there will be a tornado in Toronto," or something like this. So you see, after point for the 3 digit, it has so much problem, in the what do you call, in the weather forecast. Therefore, systems engineer, we should not actually we should not overlook something. So that's the main reason behind it. And you see, there is a very nice example. Is also from a book. James Gleick, his name, and this author also, it's a very old book, I think 1960 or 50 book. And he has shown that, you see, like when we are heating the liquid, the initial stage, you see how this one is circulating. The heat is actually like, even though this is also can be seen when you are heating something in your in a pot into the kitchen. So the heat transfer is something like linear. But you see, when we are making more heat, the same thing is so disturbed. But the finding of Lawrence was that the disturbed thing, the chaos thing, also has some kind of like, if you consider, you cannot really predict the chaos chaotic system, but you can understand the pattern. So if you find out the boundary of the chaos, then you can predict still something from there. So that's actually the butterfly effect is. And here is also very interesting thing. In aircraft, we are always trying to find out the laminar flow, like undisturbed airflow. So as good as it is possible. But you see, the birds, they are actually doing a little bit opposite. They are taking the advantage of turbulent flow, but in the aircraft we cannot do the thing. So this is system thinkings in different level. It is not a linear thinking. So you have to connect other thing with your thinking when you are thinking of a solution. So that's actually the core of system thinking. Any question here? Okay, then we're gonna go system thinking and its parts. So with, oh my God, I didn't understand. Sorry. I will finish it in 5 minutes. Okay. Sorry, guys. So we need to consider purpose, elements, and interaction. And I will provide you the slides. So you just read it yourself, and it's not really complicated. You will understand. And if you do not understand anything, feel free to ask me anytime, even to write me. It's no problem. And there is also a nice example here, like, a cup of coffee, how you can make with top-down and bottom-up approach, because synthesis and analysis is the part of system thinking also. So that you will also see how you can do that. And if you do not understand this, also ask me in the next class. And this is actually a classroom thing I wanted to do. We wanted to use system thinking for deploying this one. This is a dryer, but I made some. Yes, next lecture we're gonna do it then. Okay, so but I actually intentionally made some mistakes here, so I'm explaining why I actually made this. As a systems engineer, you have to see and you have to ask every time to the stakeholder. Let's say here dryer means like you can see a be a hair dryer, but I put to make you guys confused. I put a hair dryer picture. So that we will discuss in the next class a little bit more. And this is also how our mind actually works. This is not so important, just for discussion I put those. And this is actually the system thinking perspective. When you do the system thinking, there are guidelines. So there are, this is explaining like the big picture, operational, functional, structural, and I think this, if you really understand this one, it will help your assignment also, the requirement engineering and everything. So in the next class, you also learn the requirement engineering. You will see there are some application of those. And there is also some examples. What does the big picture and operation, functional, structural means? You can read it through. And this is actually a homework if for you guys. So please try to see this video and make a system thinking application, like write down whatever you think of it. And yeah, so this is thinking loop. This is also self-explanatory diagram. If you give some moment, you will understand this one. And if you do not understand, ask me in the next class. And there are some system thinking tools. This is not so important, but I think it is important when you're going to apply the systems engineering or model the systems engineering. And these are the types of systems engineering. And this is critical thinking. So if you also read this, then you will understand the difference between critical thinking and system thinking. So that's all. Sorry, I didn't understand you too long. Yeah, next week we also do, and the first lecture task we also discuss in the next one, and I will be more okay. Oh.